Motivating question for this video and subsequent ones on inequalities. It's about the predictability of random samples. So if you were interested in doing some experiment or some survey where you were taking repeated independent draws from some distribution and calculating the sample mean that you got, so adding up all of the values you observed, dividing by the number of those. How predictable or how much doubt would I have about what the sample mean would be? Well, there is one trivial case. If the distribution has zero variance, all of the values are constant, they're all the same, so there is no doubt as to what the sample mean will be. So let's park that trivial case and instead focus on the case where there is some doubt. Can we put some bounds on what the values might be, which I would calculate the sample mean, or how likely it would be to be larger than something, or smaller than something, or between some values? And intuitively, larger samples should be more predictable. There's a reason why economic surveys are not based off one or two businesses, they're based off thousands to estimate a country's economic performance. And also, samples and distributions with lower variance should be more predictable. So let's take a simple case here of a continuous random variable x with density function f of x. So I'm going to assume here that it only takes non-negative values, x. So if I pick a positive value a, then I'll work out the expectation of x, which is defined as integrating x times its own density function, xf of x, with respect to x over all non-negative values, 0 to infinity. And given I've picked a positive point a, I can split the interval 0 to infinity as 0 to a plus a to infinity. Now I can introduce the inequality because I don't know what that first term is, and after the last equal sign, the integral of x, f of x between 0 and a, but it isn't negative because the density function isn't negative, x between 0 and a isn't negative, so it's, well, could be 0 or could be positive. So I know that the expectation of x has to be greater than or equal to the integral of x, f of x, with respect to x between a and infinity. Now, on that interval between a and infinity, then x is bigger than a. I know that because the smallest value x takes on the interval a to infinity is a. So I can state that the integral of x, f of x, with respect to x between a and infinity is bigger than or equal to the integral of a, f of x, between a and infinity. A is just a constant, so I can pull it out the front of the integral sign. And what I will get to at the end is that the expectation of x has to be greater than or equal to a times the integral of the density function between a and infinity. So if I just rearrange this, division by the positive value a just gives me that the expectation of x divided by any positive point a has to be greater than or equal to the probability that the variable x is greater than or equal to a. And this is known as Markov's inequality. Now, the proof we've done here is only for continuous variables with density functions and integrals. But in fact, the proof's basically the same for discrete random variables. Obviously, where I've got a density function, I've got a probability mass function for the discrete case, and everywhere I'm integrating, I would be summing over those probability masses. But the proof is essentially the same. And credit where credit's due, this long dead bearded Russian, Andrei Markov.